Welcome to BVR Physics and Chemistry Made Easy. Today our topic is about refraction of light at plane surface. It's not about reflection of light, it is about refraction of light. What do you mean? What is the main difference between these two? Suppose there is a surface over here like this. If an incident ray hits this surface and bounces back like this is called incident ray and this is called reflected ray. This phenomena is called reflection. Okay, today our topic is what? Refraction. Now let us not consider this as a smooth surface. Let us take it like a bucket filled with water. A bucket is filled with water. So water is up to here. This is called interface. You remember this, very important to remember. This is called interface. This point is called interface. Means what? Above the water level it is air and below the water, this level, below this point it is water. So you have two medias over here. This happens in case of refraction. So what happens? Instead of bouncing back, ray travels into the other media. This is one media and this is another media. So ray is traveling, instead of going away straight also, it bends, and we'll see why it bends and all that. This bending of a light ray is called refraction. Bouncing back of a light ray is called reflection. So our topic is refraction. So why does the light refract? Why does the light bend? Now this is the same. This is lens. So this is almost related to lens, refraction. If we speak about reflection, then it will be about mirror, a plane mirror, where we find our own image, reflection. Very good. So now coming to this, why a ray bends? It bends because of refractive index. Because of refractive index. Each material has its own refractive index. Now air refractive index is 1.0003 and refractive index of water is 1.33. Refractive index of kerosene is 1.44 and the refractive index of glass is 1.5. So more the refractive index, lesser is the velocity of light. Right? Lesser the refractive index, more is the velocity of light in that particular media. So what happens now? I told you like this. That means refractive index is inversely proportional to velocity. Right? That means if the refractive index of one particular media is more, then automatically velocity will be less. Right now, it is compared with what? C. On the top it should be C. So refractive index is a ratio, C by V. It's a ratio of velocity of light in, this is in vacuum, velocity of light in vacuum compared with velocity of light in any media, other than vacuum. Okay, and C particular stands for what? Velocity of light in vacuum is 3 into 10 to the power of 8 meter per second. That is nothing but 3 lakh kilometer per second. So this is what you mean by refractive index, a very important point. Now what is the relationship between N and V? N is refractive index. Inversely, see inversely. That means if refractive index increases, automatically velocity will decrease. If refractive index decreases, means automatically velocity will increase. Right? Now we will see how it is. Suppose say I am taking water, a bucket full of water. So this is called interface. This point is called interface. Same way, this is called interface. What did I speak about interface? Suppose I took a bucket with water up to here. This point is called interface. This one only. Above this, what you find? Air. Below this, what you find? Water. Therefore, these are two media. This is one media and this is another media. Right? Like this. So that point is called interface or partition. Partition is called interface. Now I took interface. Imagine this side is denser. So this part is denser. Means it's filled with water. So we consider as denser. The above one is called as rarer. Same way, let me now take this part as denser. This is denser for me. Okay. Now means I am taking a transparent glass. So I am allowing light to fall like this. So it's from rarer to denser. Then the same light now it is coming out here. Therefore it is coming out from what now? Denser to rarer. So same topics. Therefore this part will be denser for me. This is denser and this is rarer. So Right, very good. Now what is happening? Let us see. So this is the incident ray. This ray is actually supposed to go away like this. This going supposed to go away, you have to show, otherwise there is no meaning at all. So light, you are sending a light ray from denser to rarer. See, you look at the arrow, you will understand my concept. So I am sending a light ray from denser to rarer. So it's denser to rarer, my topic is. Now what is happening over here? I am sending a light ray. This indicates that incident ray. This is an incident ray. Here also it indicates incident ray only. It is traveling from denser to rarer. See, D to R. And arrow also very clear that denser to rarer. Now in this case what happens? It is moving from rarer to denser. So this should. So at this point I have to draw a normal. So at this point I have to draw a normal. Now you tell me what is the concept over here? Light is traveling from rarer to denser. That means your n value, n is equal to C by V. So this is in air, yes, rarer. Then it is coming into denser. See, if I can move very easily on the floor, outside, right? Can I maintain the same speed in the swimming pool? No, I cannot maintain because that is denser. It is some liquid is there, okay? That will reduce my speed. Same. So when the light is traveling from rarer to denser, its speed will be reduced. Why it will be reduced? Because now I told you, no, refractive index of this water is greater than air. Refractive index of air is 1 only 1. While refractive index of water is 1.33 more. So refractive index, when you compare, we speak about this line, right, R to D. So refractive index will increase when it comes from R to D. Refractive index increase, automatically velocity will decrease. Therefore, instead of going in its own path, it will deviate towards normal. It will move towards normal. So when I am rubbing it, okay, when a light is traveling from rarer to denser, it moves towards normal. It moves towards normal. Why it moves towards normal? If you want, I will show you once again. N is equal to C by V. Velocity, see, refractive index of air is just 1. Refractive index of water is 1.33. More. Refractive index is more. So refractive index is more, velocity will reduce. Therefore, it bends towards normal. It will bend towards normal. Come to this point. Already it is coming from denser to rarer. So refractive index of water will be 1.33. Then it is again coming out into 1.0003. But still we consider it as simply 1. So it is moving from higher refractive index to lower refractive index. Higher refractive index to lower. Final one is lower refractive index. Then its velocity will be more. Quite opposite. So instead of going away like this, it will bend away from normal. This angle will be more. It will bend away from this normal point. Here in this case is what is happening, and so simple, so clear it is. Rarer it is, rarer. Its refractive index is just 1.00, while refractive index is 1.33. So when it is coming right like this from rarer to denser, refractive index is increasing. Therefore, it is told that velocity will decrease. Yes, velocity, instead of going away like this, its velocity decreases, so it moves towards the normal. Now, in this case, what is happening? It is coming from denser to rarer. Since it is coming from denser to rarer, that is 1.33 to 1. So, refractive index here it is decreasing when velocity increases. When velocity increases, automatically it will move away from normal. So this angle will be more. This is about refraction, right? Now we'll see critical angle and then total internal reflection. What does critical angle means? So see, previously I was telling you, I took a denser media on the top, same way. What is critical angle? What actually you mean by that word critical? Difficult angle, difficult to get, critical position. Okay, the person is in critical condition, means can't say like that. Okay, so this is like interface. Just now I told you, interface. This is what normal. It's like this normal. A very important topic. because this makes this critical angle is very important. This gives a new phenomena called as total internal reflection, due to which diamond shines, right? Diamond gets that value because it shines, and that value is added because of this critical angle only. Now we'll see what is it. So you remember, if a light ray, suppose I am drawing here denser to rarer. 1 second, I want to show you. So this is interface over here and this is normal. This is denser, I told you this is denser. If a light ray travels from denser to rarer, what happens? Instead of going away like this, it will move away from normal, it will move away from normal. This is normal, okay? Instead of going away like this, it is moving away from normal. Why? Because it is coming from denser to rarer. What do you mean by denser? Refractive index is more, then what happens to its velocity? Less. That's okay. But what is happening at the end? Refractive index is becoming less because you are coming from denser to rarer. Refractive index is decreasing, therefore velocity increases. Same concept what I explained just now here, same. It is like that. Instead of going away like this, it moves away from normal because it is traveling from denser to rarer. That means what you can consider 1.33 to 1. It is traveling from 1.33 to 1. So what value is this one? N. So N is decreasing, isn't it? So same thing I showed here very clearly. See, N is decreasing. 1.33 to 1. So it's decreasing, then velocity increases, so it moves away from normal. So now this is denser, very clear. This is denser and this is rarer. Same phenomena. So this is I am sending an incident ray. So this ray is supposed to go away like this. Okay, supposed to go away like this. You have to show supposed to go. Otherwise there is no meaning at all. So what happens? It will move away from normal. Why will it move away from normal? Just now I told you, no. Denser to rarer. Almost like 1.33 to 1.00. See, this arrow shows that it is traveling from 1.33 to 1.00, the less one. So it is moving away from normal. This happens. So now let us try. So this was your angle of incident from here. Now let us try in such a way that the refracted ray travels along this interface. So I increase the angle of incident little bit. I increase the angle of incident. So when I increase the angle of incident little bit, previously it was from here. I told you, no, I marked it here. So instead of that I increase. Then what happens? Now my refracted ray. This is my refracted ray. Okay, I'll rub all this. So this is my refracted ray. So instead of going into the rarer medium like this, now it is no more going. See, I am showing you very clearly, no more going. It is traveling along the interface, and I got an angle of refraction as how much? 90 degree. If I get an angle of 90 degree, how will I get 90? If the ray travels along the interface. I will get an angle 90 over here, which is angle of refraction. For this particular angle of refraction, whatever the angle of incident is there, no, that is called critical angle. This is also angle of incident only. Once again, see, this is also angle of incident. For particular angle of incident, if angle of refraction is 90, then this is no more called as angle of incident. This is called as critical angle. Clear? Is it clear? Once again I will tell you. For a particular angle of incident, this is angle of incident only. So actually what happens? Ray is supposed to go away like this. Okay, like this it will go away, but it will not go in its path. It will move away from the normal. So you are trying and making the ray to travel along interface. If you are getting it, then the angle of refraction is 90. Then this angle of incidence is no more called angle of incident. This is called critical angle. That is what you mean by critical angle. Means it is also an angle of incident only. For a particular angle of incident, if angle of refraction is 90, then this angle of incident is called critical angle. Okay. Now we will see next phenomena, total internal reflection. Now let me explain you about total internal reflection. So just now we have seen formation of critical angle. Now I will explain you total internal reflection, due to which actually diamond shines. The brilliance of diamond is because of total internal reflection. And your fiber optics, okay, all this works under total internal reflection. Now I will show you how it is. So just now I said no, this is called interface, and this is interface. And remember, total internal reflection takes place when the light ray travels from denser to rarer. Very clear, not from rarer to denser. No, it is from denser to rarer. So let us take this as denser. This is denser, and this is rarer. What rarer means? Air, you can consider air. Denser means you can consider water. What did I tell you? Refractive index of water is 1.33 while air is 1.0003. So you can simply treat it as 1. Right. This is what? Normal over here. See, this is denser, understood. Now this is the incident ray. This is an incident ray. Okay, incident ray. It is supposed to go away what? Like this. It is supposed to go away like this. Yes. Supposed to go away like this. Yes. Now what is happening? Since the light ray is moving from denser to rarer, so when a light ray moves from denser to rarer, it moves away from the normal. So if you take this as denser and rarer, and this is normal, when you send a light ray from here, incident light ray from denser to rarer, I told you n is equal to c by v. So rarer means refractive index will be less and velocity will be more. So velocity, so instead of going towards normal, it will go away from normal. This angle will be more. So what I mean to say, it's like this. So this angle will be more. This angle will be more because it is moving away from normal. Why is it moving away from normal? Because it is traveling from, you can look at this one. By looking at this, you will understand. It is traveling from denser to rarer. But what happens, just now we have seen, if you can try it out, okay, with great interest, if you can increase or decrease the angle of incident, particularly for a particular angle of incident, this is nothing but angle of incident only. This is nothing but angle of incident. If suppose you send an angle of one incident ray, and if that ray happens to travel along the interface, if that ray travels along the interface, if it is traveling along the interface, please remember this one, if it is traveling along the interface, then angle of refraction here will be 90. Angle of refraction will be 90 degree. So what is happening? Come on, tell me. Just now what I explained is critical angle. I am explaining you again, because if I explain you critical angle only, you will understand what is total internal reflection. See, this is a particular angle of incident for which angle of refraction you got 90. That means your refracted ray is traveling along the interface. So you got it as 90. Therefore, this angle of incident is called as critical angle. This angle of incident is called as critical angle. If you increase the angle little more than critical angle, if you are increasing the angle little more than critical angle. Now see, this is your incident ray. This is your incident ray. And this is your normal. Now see the angle. This angle, very clearly it is mentioned, please look here. This is angle of incident. This angle of incident is greater, this indicates greater than critical angle. If you increase the angle which is greater than critical angle, see, I am doing like this. This is your angle of incident for which angle of refraction 90 you got, therefore you are calling it as critical angle. If you increase the angle more than critical angle, so instead of ray going along the interface, it will bounce back into the same media. This is called total internal reflection. So what happened? How did you get total internal reflection? So you got for a particular angle of incident, angle of refraction is 90 because the ray is going along the interface, so angle of refraction is 90. Suppose you are getting your angle of refraction 90 when the light ray travels along the interface, then that angle of incident is called critical angle. If you increase the angle more than this critical angle, okay, then ray instead of going into the other media or traveling along the interface, it will go into the same media, back again into the same media. That is called total internal reflection.